Hello, everyone. Well, I'm going to be this afternoon going over a piece that I wrote recently called What Ultimately Is There? Metaphysics and the Ruliad. I wrote this piece partly as a result of a grant that we got at the Wolfram Institute for Computational Metaphysics. This was sort of intended to be the beginning of a discussion with traditional experts in philosophy about the kinds of things that we're doing. So let me tell you what I had to say there. So, first topic is moving metaphysics from philosophy to science. What ultimately is there has always been seen as a fundamental, if thorny, question for philosophy or perhaps theology. But despite a couple of millennia of discussion, I think it's fair to say that only modest progress has been made with it. But maybe, just maybe, this is the moment where that's going to change, and on the basis of surprising new ideas and new results from our latest efforts in science, it's finally going to be possible to make real progress, and in the end to build what amounts to a formal scientific approach to metaphysics. It all centers around the ultimate foundational construct that I call the Ruliad, and how observers like us, embedded within it, must perceive it. And it's a story of how, for observers like us, fundamental concepts like space, time, mathematics, laws of nature, and indeed objective reality must inevitably emerge. Traditional philosophical thinking about metaphysical questions has often become polarized into strongly opposing views. But one of the remarkable things we'll see is that with what we learn from science, we'll often be able to bring together these opposing views, typically in rather unexpected ways. I should emphasize that my goal is to summarize what we can now say about metaphysics on the basis of our recent progress in science. It'll be very valuable to connect this to historical positions in historical thinking in philosophy and theology, but that's not something I've yet attempted to do. So I should also say that I'm going to concentrate on sort of the major intellectual arc of what one can think of as a new scientific approach to metaphysics. The technical details of the science, well, I've mostly talked about elsewhere. The foundations of physics. We're going to begin our journey by talking about the traditional objective of physics to find abstract theories that describe what we observe and measure in the physical world. From the history of physics, we've come to expect that such theories will always end up being at best successor approximations. But the new possibility raised by our physics project is that we may now finally have reached the end, a truly fundamental theory of physics that provides a complete description of the lowest level machine code of our universe. Already in antiquity, the question arose of whether the universe is ultimately a continuum or is made of discrete atomic elements. By the end of the 19th century, it was finally established that matter at least consists of discrete elements. And soon it became clear that light could be thought of in the same way. But what about space? Ever since Euclid, it had been assumed that space was a continuum, and efforts in the early 20th century to see whether it, like matter, might be discrete did not work out. But a century later, building on new computationally inspired ideas, our physics project starts from the concept that space is not just a simple continuum. Instead, it's a complicated, discrete structure that in fact represents every aspect of our universe, both what we normally think of as space and everything in it. There are many ways one can imagine describing this structure. A convenient one is to say that it consists of a very large number of discrete, intrinsically identical atoms of space that one can think of as being like disembodied geometrical points, whose only property, other than being distinct, is how they're abstractly related to other atoms of space. In other words, we imagine describing the whole structure of the universe in terms of the pattern of relations between the atoms of space. And it's conventional to represent this as a hypergraph whose nodes are atoms of space and whose hyperedges define the relations between them. If the relations are only between pairs of nodes, this becomes just an ordinary graph. So an important piece of intuition that comes from our practical experience with computers is that it's possible to represent everything we deal with in terms of bits. But when we also want to represent the structure of space, it's better to think not in terms of bits in some predetermined arrangement, but instead in terms of the lower level and more flexible kind of data structure defined by a hypergraph. So how can the universe as we normally perceive it emerge from this? It's very much analogous to what happens with matter. For example, even though something like water consists of discrete molecules, the aggregate effect of them is to produce seemingly continuous fluid behavior. But then, still made up of the same underlying molecules, we can have discrete eddies in the fluid, analogous in the case of space to particles like electrons, or for that matter, black holes. Time and spacetime. If there's a hypergraph that's the ultimate data structure of the universe, what are the algorithms that get applied to it? Just as we imagine the data structure to consist of discrete elements, so also we imagine that changes to it occur by discrete events. And for now, we can imagine that there's some fixed rule that determines these elementary events. For example, the rule might be that whenever a piece of the hypergraph has some specified form, it should be replaced by a piece of hypergraph with some other specified form. We can think of the application of such a rule as corresponding to the computation of the next state of the universe from the previous one. And if the rule is repeatedly applied, it will generate a whole sequence of updated states of the universe. And we can then identify the progression of these states as corresponding to the progression of time in the universe. It's notable that in the setup, space and time are, at least at the outset, different kinds of things. Space is associated with the structure of the hypergraph, yet time is associated with computation on it. Still, just as the hypergraph defines relations between atoms of space, we can imagine a causal graph that defines causal relations between events. Any particular event can be thought of as taking some collection of atoms of space as inputs and producing some other collection of atoms of space as outputs. But this then implies a causal relation between events. Any event that uses as input an atom of space that was generated as output by another event can be thought of as causally dependent on that other event. And the whole pattern of these causal relations ultimately defines a causal graph for all events in the universe, that in a sense encodes the structure of the universe in both space and time. But given such a causal graph, can we reconstruct a series of hypergraphs from it? We can think of such hypergraphs as representing successive instantaneous states of space. And, just like in relativity, it turns out that there isn't a unique possible such sequence of states. Instead, there are many different sequences, all consistent with the underlying causal graph and corresponding in traditional physics terms to different relativistic reference frames. Well, in effect, therefore, we can think of the causal graph as being the true representation of information about the universe. Any particular reconstructed sequence of hypergraphs inevitably involves arbitrary choices. When we introduced the causal graph, we were talking about building it by starting from a particular hypergraph and then looking at the effect of applying rules to it. But the point is that it turns out that there's a lot of choice in both the hypergraph and how we apply the rules. But as a result of the phenomenon called causal invariance, essentially all choices will lead us to the same causal graph. We might have imagined that given a fundamental theory of physics, we should be able to ask what the universe in some sense statically is. But what we're discovering is that we should instead be talking about the processes that happen in the universe as represented by the causal graph. We can identify the passage of time as the progression of events in the causal graph, but why is there even something like space? Ultimately, it turns out to be a reflection of the entanglement of different sequences of events in the causal graph, and its structure is in effect a map of the relations between these sequences of events, a structure that can be conveniently represented by a hypergraph. So imagine starting from one event in the causal graph, then tracing a sequence of events that depend on it. We can think of the successive events as occurring progressively later in time. But what about two events that are both immediate successors of a given event? What is their relationship? The key idea is that even though these sibling events occur at the same time, they are still separated in what we can think of as space. But how then is space as a whole formed? Ultimately, it's something very dynamic. And indeed, it's the continual occurrence of events in the universe that knits together the structure of space. Without such activity, there will be nothing we could coherently consider as space. At the level of atoms of space, there's nothing permanent in the universe. In every elementary event, atoms of space are destroyed and new ones are created. But somehow at an aggregate level, there's a certain stability to what emerges. It's again a little like with fluids, where the microscopic motions of huge numbers of underlying molecules lead in the aggregate to the laws of fluid mechanics. But what then are the aggregate laws that emerge from large numbers of hypergraph updates? Remarkably enough, they almost inevitably turn out to be exactly the Einstein equations, the equations that seem to govern the large-scale structure of space-time. So even though what's there underneath is just what we might think of as abstract atoms of space and rules for rewriting relations between them, what emerges is something that reproduces familiar elements of what we think of as physical reality. The phenomenon of computational irreducibility. If there's a rule that can ultimately reproduce the behavior of the universe, how complicated a rule does that need to be? Our traditional intuition, say from experience with engineering, is that one needs a complicated rule if one wants to produce complicated behavior. But my big discovery from the early 1980s is that this isn't the case, and that in fact it's perfectly possible for even extremely simple underlying rules, like my favorite Rule 30, to produce behavior of immense complexity. But why ultimately does this happen? We can think of running a rule as being like running a program, or in other words, like doing a computation. But how sophisticated is that computation? We might have thought that different rules would do incomparably different computations. But the existence of universal computation, discovered a century ago, implies that in fact there's a class of universal rules that can effectively emulate any other rule, and this is why, for example, software is possible. But actually, there's a lot more that can be said. And in particular, my principle of computational equivalence implies that essentially whenever one sees a system whose behavior is not obviously simple, the system will actually be doing a computation that is in some sense as sophisticated as it can be. In other words, sophisticated computation isn't just a feature of specially set up computer-like systems, it's ubiquitous even among systems with simple underlying rules. So what does this mean? It's often considered a goal of science to be able to predict what systems will do, but to make such a prediction requires, in a sense, being able to jump ahead of the behavior of the system itself. But the principle of computational equivalence tells us that this won't in general be possible, because it's ubiquitous for the system we're trying to predict to be just as computationally sophisticated as the system we're trying to use to predict it. And the result of this is the phenomenon of computational irreducibility. You can always find out what a system will do just by explicitly running its rules step by step. But if the system is computationally irreducible, there'll be no general way to shortcut this and to find the result with reduced computational effort. Computational irreducibility is what irreducibly separates underlying rules from the behavior they produce. And it's what causes even simple rules to be able to generate behavior that cannot be decoded except by irreducibly great computational effort, and therefore will be considered random by an observer with bounded computational capabilities. Computational irreducibility is also what, in a sense, makes time something real. We talked about before the fact that the passage of time corresponds to the progressive application of computational rules. Computational irreducibility is what makes that process add up to something. And the principle of computational equivalence is what tells us that there's something we can think of as time, that it is in effect pure irreducible computation, independent of the system in which we're studying it. It's very much the same story with space. Computational irreducibility in general leads to a certain uniform effective randomness in the structure of hypergraphs, which is what allows us to imagine that there's a definite kind of substrate-independent concept of space. There's a close analogy here to what happens in something like a fluid. At the molecular level, there are lots of molecular collisions going on, but the point is that this is a computationally irreducible process whose end result is enough uniform effective randomness that we can meaningfully talk about the properties of the fluid in bulk as a thing in itself without having to mention that it's made of molecules. So how does all this relate to the original metaphysical question of what there ultimately is? Computational irreducibility introduces the idea that there's something robust and invariant about pure computation, something that doesn't depend on the details of what's implementing that computation. Or in other words, that there's a sense in which it's meaningful to talk about things simply being made of computation. The significance of the observer. In talking about things like a hypergraph representing space and everything in it, we're giving, in a sense, an objective description of the universe from the outside. But what ultimately matters to us is not what's in principle out there, but rather what we actually perceive. And indeed, we can think of science as being first and foremost a way to find narrative descriptions which fit in our minds of certain aspects of what's out there. But given computational irreducibility, why is this even possible? Why are there ever, for example, laws of nature which let us make predictions about things, even with the bounded amount of computation that our finite minds can do? The answer is related to an inevitable and fundamental feature of computational irreducibility, that within any computationally irreducible process, there must always be an infinite number of pockets of computational reducibility. In other words, even though computational irreducibility makes it irreducibly difficult to say everything about what a system will do, there will always be pockets of reducibility which allow one to say certain things about it. And it's such pockets of reducibility that our processes of perception and our science make use of. Once again, we can use fluid dynamics as an example. Even though the detailed pattern of underlying molecular motions in a fluid is computationally irreducible, there are still computationally simple overall laws of fluid flow that we can think of as being associated with pockets of computational reducibility. And from our point of view, as computationally bounded observers, we tend to think of these as the laws of the fluid. In other words, the laws we attribute to a system depend on our capabilities as observers. Consider the second law of thermodynamics, and imagine starting from some simple configuration, say, of gas molecules. The dynamics of these molecules will generically correspond to a computationally irreducible process, whose outcome to a computationally bounded observer like us will seem increasingly random. Of course, if we were not computationally bounded, then we'd be able to decode the whole underlying computationally irreducible process, and we wouldn't believe in the presence of seemingly increasing randomness, or for that matter, the second law. But regardless of any details, as soon as we're computationally bounded, we'll immediately perceive the second law. We might have assumed that the second law was some kind of intrinsic law of nature directly related to what there ultimately is. But what we see is that the second law is something that emerges because of us and our characteristics as observers, and in particular, our computational boundedness. There are other things that also work this way. For example, our belief in a coherent notion of space. At the lowest level, we imagine that there's a discrete hypergraph being updated through what's ultimately a computationally irreducible process. But as computationally bounded observers, we only perceive certain aggregate features that correspond in effect to a pocket of computational reducibility associated with our simple continuous perception of space. When we think about space-time, and for example about deriving its relativistic properties, there's another feature of us as observers that also turns out to be important. The fact that we assume that we are persistent in time, and that even though we might be made of different atoms of space at every successive moment of time, we can still successfully knit together perceptions of at successive moments of time to form a single thread of experience. In a sense, this is a simplification forced on us by our computational boundedness, but it's also in many ways at the core of what we think of as our notion of consciousness, which is something I've written about at some length elsewhere. The principle of computational equivalence implies that sophisticated computation is ubiquitous, and certainly not something special to brains. And indeed, it seems that brains actually concentrate on a specific and in many ways limited form of computation. They take in large amounts of sensory data and in effect compress it to derive what's ultimately a thin stream of actions for us to take. At a biological level, there's always all sorts of activity going on across the billions of neurons in our brains. But our brains are, it seems, specially constructed to concentrate all that activity down to what's essentially a single thread of thought, action, and experience. And it's the fact that this is a single thread that seems to give us our sense of coherent existence and an effect of consciousness. Quantum mechanics and multiway systems. Traditional classical physics talks about definite things happening in the universe, say a projectile following a definite path, determined by its laws of motion. But quantum mechanics instead talks about many paths being followed, specifying only probabilities for their various outcomes. In in the history of physics, the quantum mechanics was a kind of add-on. But in our physics project, it's immediately essential and unavoidable because the rules that we define simply say that whenever there is a piece of a hypergraph that matches a particular pattern, it should be transformed. But in general, there will be many such matches, each one producing a different transformation, and each one, in effect, initiating what we can think of as a different path of history. And in addition to such branching, there can also be merging when different transformations end up producing the same hypergraph. We can represent all these branching and merging paths of history by what I call a multiway graph. And we can think of such a multiway graph as giving a complete description of what happens in the universe. But as we talked about before, observers like us maintain just a single thread of experience. And that means we can't directly perceive the whole multiway graph. Instead, we have to effectively pick out just one path from it. But which path will it be? At the level of the formalism of quantum mechanics, or of our physics project, the only thing we talk about is the whole collection of all paths. So something else must determine the path. In physical space, we're used to the idea that we as observers are localized at a particular position and only get to directly perceive what's around where we are. Across all of physical space, there are lots of things going on, but because of where we happen to be, we only get to directly perceive a tiny sample of them. So is something similar going on in picking paths of history from the multiway graph? It seems that it is. If we take a slice across the multiway graph at any particular time, we'll have lots of dangling ends of paths of history, each associated with a different state of the universe. But inevitably, there are lots of relations between these states. For example, two states might have an immediate common ancestor. And it turns out that we can think of the states as being laid out in what we can call branchial space. And just like in physical space, we can expect that we as observers are localized in branchial space. So that means that even though there are at some level many different paths of history, we only get to perceive ones that are around where we are. And just like there's no theory that tells us where we find ourselves in physical space, which planet, which galaxy, and so on, the same is true in branchial space. One day we might have some way to describe our location in branchial space, but for now, the best we can say is that it's random. And this, I believe, is why outcomes in quantum mechanics seem to us random. The whole multiway graph is completely determined, as wave functions and so on are even in the standard formalism of quantum mechanics. But which part of the multiway graph we as observers sample depends on where we are in branchial space. And we can expect that just as we humans are all close together in physical space, so are we in branchial space. And this means that even though in the abstract, the result of, say, some particular quantum measurement might seem random, all human observers, being nearby in branchial space, will tend to agree what that result is. And at least among them, there'll be something they can consider objective reality. The concept of the Ruliad. The remarkable implication of our physics project is that our whole universe, in all its richness, can emerge just from the repeated application of a simple underlying rule. But which rule? How would it be selected? The idea of the Ruliad is to imagine that no selection is needed because all rules are being used. And the Ruliad is what comes out, the entangled limit of all possible computational processes. We talked about, in the context of quantum mechanics, the idea that a given rule can get applied in multiple ways, leading to multiple paths of history. The Ruliad takes this idea to the limit, applying not just one rule in all possible ways, but all possible rules in all possible ways. We can imagine representing the Ruliad by a giant multiway graph in which there's a path that represents any conceivable specific computation. And what fundamentally gives the Ruliad structure is that these paths can not only branch, but also merge, with mergers happening when different states lead to equivalent outcomes which are merged in the multiway graph. At first, we can think of the Ruliad as being built from all possible hypergraph rules in our physics project, But the principle of computational equivalence implies that actually we can use any type of rule as our basis. Since the Ruliad contains all possible computational processes, its final form will be the same. In other words, however we end up representing it, the intrinsic form of the Ruliad is still the same. Once we have the concept of computation, or of following rules, the Ruliad is an inevitable consequence. In some sense, it is the ultimate closure of the concept of computation, the unique object that encapsulates all possible computational processes and the inevitable relations between them. We got to the Ruliad by thinking about physics and about the ultimate infrastructure of our physical universe. But the Ruliad is something much more general than that. It's an abstract object that captures everything that is computationally formalizable, along with the elaborate structural relations between such things. Of course, the idea that the Ruliad can describe our actual physical universe is ultimately just a hypothesis, though one that's strongly encouraged by the success of our physics project. How could it be wrong? Well, our universe could involve hypercomputation, which is not finitely captured by the Ruliad, and we might have to consider a whole hierarchy of possible hyper-Ruliads, though, as we'll talk about, any effects from this would likely be beyond anything observers like us could perceive. But assuming that the Ruliad is the ultimate infrastructure for everything, we can then ask what it's made of. At some level, we could just say it's made of abstract computational processes. But what are those processes operating on? Again, abstract things. But we can imagine decomposing those abstract things. And while inevitably there will be different ways to do this, it'll often be convenient to imagine that they consist of relations between they consist of relations between ultimate indivisible objects, which we can describe as atoms of existence, or what I've called Emes, E-M-E-S. In our physics project, we identified Emes with atoms of space. But in talking about the Ruliad in general, we can think of them just as the ultimate raw material for existence. Emes have no structure of their own. And indeed, the only intrinsic thing one could say about them is that they are distinct. In a sense, they are elementary units of identity. And we can think of it as being the relations between them that build up the Ruliad and everything it underlies. Observers in the Ruliad and the laws of nature. Our original metaphysical question was, what ultimately is there? And at some level, our science has now led us to an answer. The Ruliad is everything there ultimately is. But what about what there is for us? In other words, what about what there ultimately is in what we perceive and experience? Inevitably, we as observers must be part of the Ruliad, and our inner experiences must similarly be represented within the Ruliad. But in and of itself, there's not enough to tell us much about what those experiences might be. And we might imagine that to work this out, we'd need to know a lot about the particular details of our construction and our place in the Ruliad. But what's emerged in the last few years is that in many important ways we don't. And instead, just knowing a certain coarse features of us as observers already implies a lot about what we must experience. In particular, if we assume that we are observers who are computationally bounded and believe we are persistent in time, then we argue that it's inevitable that we must perceive certain laws to be operating, and those laws turn out to be exactly the three central laws of 20th century physics: general relativity, quantum mechanics, and the second law of thermodynamics. It's a remarkable claim. The laws of physics we observe don't just happen to be the way they are inevitable for observers with the general characteristics we have. At the level of the underlying Ruliad, the laws of physics that we might observe are not determined. But as soon as we know something about what we are like as observers, then we necessarily end up with our familiar laws of physics. In a sense, therefore, the laws of physics that we experience are the way they are because we are observers because we are observers that are the way we are. So we already talked about before that in the case how this works in the case of the second law, and although we don't yet know all the details, the basic conclusion is that by combining the abstract structure of the Ruliad with our assumptions about what we are like as observers, we're able to derive all three of the familiar core laws of physics from the 20th century. It's worth emphasizing that what we can immediately derive are, in a sense, general laws. We know that space-time has a certain overall structure and its dynamics satisfy the Einstein equations. But we don't know, for example, why the universe as we perceive it has, at least approximately, 3 dimensions of space. Though actually my guess is that many such features of observed physics can ultimately be traced to features of the way we are as observers. So what about observers not like us? They're still part of the Ruliad, but in a sense they're sampling it in a different way, and they'll potentially perceive quite different laws of physics. It's a very fundamental observation about our universe that we perceive it to follow fairly simple laws. But in a sense, this too is just a feature of our nature as observers, because given our computational boundedness, we couldn't really make use of or even identify any laws that were not in some sense simple. The fact that simple laws are possible can be viewed as a reflection of the inevitable presence of pockets of computational reducibility within any computationally irreducible process. But it's our computational boundedness as observers that causes us to pick them out. If we were not computationally bounded, then we could operate at the level of raw computational irreducibility and not need to pick out simple laws. At the outset, we might have imagined that the laws of physics would somehow be fundamentally at the root of the question of what ultimately is there. But what we're seeing is that actually these laws are, in a sense, higher level constructs whose form depends on our characteristics as observers. And to get to our original metaphysical question, we have to drill down beyond our perceived laws of physics to their computational infrastructure all the way to the Ruliad, ultimately all the way to the Ruliad. The question of objective reality. When we ask what there ultimately is, we're in some sense implicitly assuming that there actually is something definite, or in effect, that there's a single ultimate objective reality. But is that actually how things work, or does every observer, for example, in effect have their own reality? In our approach, there's a quite nuanced answer. At the very lowest level, there is a single ultimate objective reality that knits everything together, and it's the Ruliad. But meanwhile, different observers can in principle experience different things. But as soon as we're dealing with observers even vaguely like us, in the sense that they share our computational boundedness and our belief in our own persistence, we've argued that it's inevitable that they'll always experience the core laws of physics as we know them. In other words, these laws in effect represent a single objective reality, at least across observers even vaguely like us. But what about more detailed features of our experience? No doubt we'll be able to objectively derive on the basis of characteristics we identify as shared across all observers, some more detailed features of our experience will be able to objectively derive on the basis of characteristics we identify as shared across all observers like us. But at some level, different observers will always have different experiences, not least because, for example, they're typically operating at different places in space, and indeed in general at different places in the Ruliad. Still, our everyday impression is that even though the detailed experiences, say, of different people looking at the same scene may be different, those experiences can nevertheless reasonably be thought of as all derived from the same underlying objective reality. So why is this? Essentially, I think it's because human observers are all very nearby in the Ruliad. So they're, in a sense, all sampling the same tiny part of the Ruliad. Observers at different places in the Ruliad, in effect, sample different threads of history that operate according to different rules. But the principle of computational equivalence tells us that just as it's always possible to translate from one universal computational system to another, it'll always in the end be possible to translate between what observers get by sampling at different places in the Ruliad. The difficulty of translation depends, though, on how far one is trying to go in the Ruliad. Human minds exposed to similar knowledge, culture, and so on are nearby and fairly easy to translate between. Animal minds are further away and more difficult to translate to. And when it comes to something like the weather, then even though in principle it's computationally equivalent, the distance one has to go in the Ruliad to reach it is sufficiently great that translation is very difficult. Translation between places in the Ruliad is in a sense just a generalization of translation in physical space. And the process of moving in physical space is what we describe as motion. But what actually is motion? In effect, it's having something move to a different place in space while still being the same thing. In our physics project, though, something must be made of different atoms of space if it's at a different place in space. But somehow there must be some pattern of atoms of space that, a bit like an eddy in a fluid, one can say represents the same thing at different places in space. And potentially, we can think of particles, like electrons or photons, as being, in a sense, elementary carriers of pure motion, minimal objects that can move without changing. But how does this work more generally in the Ruliad? What is it that can move between observers or between minds without changing? Essentially, it seems to be concepts, often in basic form represented by words. Within, for example, one human brain, a thought corresponds to some complicated pattern of neural activity. But what allows it to be moved to another brain is packaging it up into a concept that can be unpacked by another brain. And at some level, it's this kind of communication that aligns observers to have similar inner experiences to the point where they can be viewed as reflecting a common objective reality. But all of this somehow presupposes that there are many observers whose experiences can be thought of as triangulating to a common objective reality. If there were just one observer, though, there's no triangulation to do, and one might imagine that all that would matter is the inner experience of that one observer. So in a sense, the very notion that we can usefully talk about objective reality is a consequence of there being many similar observers. And of course, in the specific case of us humans, there are indeed billions of us. But from a fundamental point of view, why should there be many similar observers or even any observers at all? As we talked about before, the core abstract characteristic of an observer is its ability to equivalence many possible inputs to produce a small set of possible outputs. And although we don't yet know how to do it, we can imagine that it would be possible to derive the fact that there must be a certain density of structures that do this within the Ruliad. Could there inevitably be enough similar observers to be able to reasonably triangulate to an objective reality? If we take the example of biology, or modern technology for that matter, it seems like what's critical in generating large numbers of similar observers is some form of replication. And so, surprising as it might seem for something as apparently as fundamental as this, it appears that our impression of the existence of objective reality is actually intimately tied up with the rather practical biological phenomenon of self-replication. Okay, so what should we in the end think about objective reality? We might have assumed that having a scientific theory of the universe would immediately imply a certain objective reality. And indeed, at the level of the Ruliad, that's true. But what we've seen is that even to get our familiar laws of physics, we need an observer parsing the raw Ruliad. In other words, without the observer, we can't even talk about fundamental concepts in physics. But the point is that for a very wide range of observers, even vaguely like us, many details of the observer don't matter. Certain things, like core laws of physics, inevitably and objectively emerge. But the laws of physics don't determine everything an observer perceives. Some things are inevitably determined by the particular circumstances of the observer, their position in space and the Ruliad, and so on. But now the point is that observers, like us humans, are nearby enough in space, the Ruliad, and so on, that our perceptions will be to a large extent aligned so that we can again usefully attribute them to what we can think of as an external objective reality. The beginning and end of time. In thinking about what there ultimately is, an obvious question is whether whatever there is has always been there and will always be, or whether instead there's in effect a beginning and end to time. As we talked about before, in our computational paradigm, the passage of time is associated with a progressive computation of successive states of the universe. But the important point is that these states embody everything, including any potential observers. So there can never be a situation where an observer could say, the universe hasn't started yet, because if the universe hasn't started, nor will the observer have. But why does the universe start at all? I'll talk about that a little bit more later, but suffice it to say now that the Ruliad in effect contains all possible abstract computations, each consisting of some chain of steps that follow from each other. There's nothing that has to actively start these chains. They're just abstract constructs that inevitably follow from the definition of the Ruliad. There'll be a beginning to each chain, though, but the Ruliad contains all possible beginnings, or in other words, all possible initial states for computations. One might wonder, given all of this, how the Ruliad can still have any kind of coherent structure. The answer, as we already talked about, is the entanglement of different threads of computation. The threads are not independent, but are related by the merging of equivalent states. Of course, one can then ask why equivalent states are in fact merged. And this is immediately a story about observers. One can imagine a raw construction of the Ruliad in which every different thread of computation independently branches. But any time states generated in different threads are identical, any observer will equivalence them. So this means that to any observer, these threads will be merged, and there will effectively be entanglement in the Ruliad. We've said that the passage of time corresponds to the progression of computation, and given this, we can imagine that the Ruliad is built up through time by progressively applying appropriate rules. But actually, we don't need to think of it this way, because once a procedure for the construction of the Ruliad is defined, it's inevitable that the whole Ruliad is, at least in principle, immediately determined. In other words, we can imagine building up the Ruliad step by step through time, or we can imagine that the Ruliad in some sense immediately just exists. But the point is that to computationally bounded observers, these are basically equivalent. In the first case, the observer is pulled along by the irreducible computation that's happening anyway to move forward the frontier of the Ruliad. In the second case, the observer in some sense has to actively explore the already formed Ruliad, but because of the observer's computational boundedness, can do so only at a certain limited rate, so that once again there is something corresponding to the passage of time and relating it to computational irreducibility. But what happens if one includes the fact that there are threads of computation in the Ruliad starting from all possible initial states? Well, a bounded observer will only be able to probe all these states and their behaviors at some limited rate. So even if from the outside the Ruliad, if one could be there, one might see infinitely many different beginnings of the universe, any computationally bounded observer embedded within the Ruliad would perceive only a limited set. And indeed, depending a bit on the scales involved, the observer might well be able to conflate those limited possibilities into the perception of just a single finite beginning of the universe, even though underneath there's much more going on in the whole Ruliad. One thing one might wonder is that since the Ruliad contains every possible rule, why can't there just be a single, very complicated rule that just creates our whole universe in a single step? The answer is that in principle there can be, but computationally bounded observers like us will never perceive it. Our narrative about the universe must involve computationally limited steps. Another subtlety concerns the relationship of time to the equivalencing of states. Imagine that in the Ruliad, or indeed just a causal graph, a particular state is generated repeatedly when rules are applied. We can expect an observer to equivalence these different instances of the state, thus in effect forming a loop in the progression of states. Quite possibly, such loops are associated with phenomena in quantum field theory, but to an observer like us, such loops will be happening at a level below perceived time. We talked about the beginning of time. What about the end? If the passage of time is the progression of computation, can the computation simply halt? The answer for any specific computation is yes. A particular rule might, for example, simply not apply anywhere in a given hypergraph. And that means that in effect, time stops for that hypergraph. And indeed, this is what presumably happens at the center of a black hole, at least in the simplest case. But what about the whole Ruliad? Inevitably, parts of it will keep running, even if some threads of computation in it stop. But the question is what an observer will perceive of that. Normally, we've just taken it for granted that an observer does what they do forever. But in reality, as something embedded in the Ruliad, an observer will at some level have to navigate computational irreducibility to maintain itself. And whether it's because a biological observer dies or because an observer ends up in a black hole, we can expect the actual span of experience of individual observers to be limited, in effect defining an end of time for the observer, if not for the whole Ruliad. Why does anything actually exist? In our discussion of what there ultimately is, an obvious question is why there's ultimately anything at all. Or more specifically, why does our universe exist? Why is there something rather than nothing? One might have imagined that there'd be nothing one could say about such questions in the framework of science, but it turns out that in the context of the Ruliad, there's actually quite a lot one can say. The key point is that the Ruliad can be thought of as a necessary abstract object. Given a definition of its elements, it inevitably has the structure it has. There's no choice about it. It's like in mathematics. Given the definitions of 1 and plus and so on, 1 plus 1 equals 2 is an inevitable consequence. It isn't a statement that needs to talk about pebbles or coins or whatever. It's an abstract and inevitable formal statement. And so it is with the Ruliad. The Ruliad has to be the way it is. Every detail of it is abstractly determined, or in other words, at least as an abstract object, it necessarily exists. But why, we might ask, is it actualized? We can imagine all sorts of formal systems with all sorts of structure, but why is the Ruliad what is actualized to give us the physical world we experience? The key here is to think about what we operationally mean by actualized. And the point is that it's not something absolute. It's something that depends on us as observers. After all, the only thing we can ever ultimately know about is our own inner experience. And for us, something is then actualized if we can, as we talked about before, successfully triangulate our experiences to let us consider it to have an objective reality. At some level, the Ruliad is an abstract thing, and our inner experiences are abstract things. And we're saying that there's a certain abstract necessity to the way these things are linked, with what amounts to a description of our physical world being a necessary intermediate step in that linking. Given its definition, it's immediately inevitable that the Ruliad must exist as an abstract object. But what about observers like us? We know ourselves that we exist from the inner experiences we have, but is it necessary that we exist? Or put another way, is it inevitable that somewhere in the Ruliad there must be structures that correspond to observers like us? Well, that's now a question we can study as a matter of science. And ultimately, we can imagine an abstract derivation of the density of different levels of observers in the Ruliad. To get observers like us requires, as we discussed above, all sorts of details, probably including features from biology like self-replication. But if we require only the features of computational boundedness and a belief in persistence, there are no doubt many more observer structures in the Ruliad. It's interesting to consider those alien minds distributed across the Ruliad. In traditional searches for extraterrestrial intelligence, one seeking to bridge distances in physical space, but likely the distances across the Ruliad and Rulial space are vastly greater, and in effect the minds are more alien, like the mind of the weather, and to communicate with them will require in effect an effort of translation that involves an immense amount of irreducible computation. But for us, and our science, what matters is our own experience. And given our knowledge that we exist, the existence of the Ruliad seems to make it in effect inevitable that we must consider the universe to exist. One wrinkle to mention concerns generalizations of the Ruliad. I talked about the fact that the Ruliad encapsulates all possible computational processes, but by this we mean processes that can be implemented on one of our traditional models of computation like Turing machines. But what about hypercomputations that will require an infinite number of steps for a Turing machine? One can imagine a whole hierarchy of hyper-Ruliads based on these. And one could imagine observers embedded not in the ordinary Ruliad, but in some hyper-Ruliad. So what will be the experience of such observers? They'd never be able to perceive anything outside their hyper-Ruliad. And in fact, one can expect that through their own hypercomputations, their perception of their own hyper-Ruliad would be essentially equivalent to our perception of the ordinary Ruliad. So that in the end, there's no perceptible distinction between being in the Ruliad and being in the hyper-Ruliad. The same universe with the same laws of physics we know exists in both. When one starts talking about the universe operating at the lowest level according to computational rules, people sometimes seem to think that means our universe must ultimately be running on a computer. But to imagine that is essentially to misunderstand the whole concept of theoretical science. But the idea in theoretical science is to construct abstract models that allow one to reproduce certain aspects of what systems do. It's not that the systems themselves mechanistically implement the models, it's just that the models abstractly reproduce aspects of what the systems do. And so it is with our model for physics. It's not that somewhere inside the universe there's a computer moving bits around to rearrange hypergraphs. Instead, it's just that abstractly rearranging hypergraphs is a way, and no doubt not the only one, of representing what's happening in the universe. Typically, the models one makes in science only aim to be approximate. They capture certain aspects one cares about in a system and idealize away all others. But our physics project is different because its goal is to make a model that, at least in principle, can reproduce in perfect detail what happens in the universe, without approximation or idealization. But what we have is still just a model, in effect a way of making a bridge from what actually happens in the universe to what we can describe in essentially human terms. There's a little more subtlety when it comes to the whole Ruliad, because while the Ruliad is precise and complete, the sampling of it that determines what we experience depends on our characteristics as observers, about which we'll never be able to be completely precise. And what's more, as we talked about before, while the Ruliad is defined in an abstract way, it's what is in effect actualized for observers like us to provide our physics and what we consider to be our it's what's in effect actualized for observers like us that provides our physics and what we consider to be our objective reality. But could all of that somehow still be a simulation running on some lower level infrastructure? Not in any meaningful sense. In talking about simulation, we're implicitly imagining that in effect the Ruliad is running in one place and other things are running elsewhere. But the Ruliad encapsulates the totality of all computational processes. So in a sense, there's no room for anything outside the Ruliad. And the only thing the Ruliad can run on is itself. Still, when it comes to observers like us, we can sample only some tiny part of the Ruliad, and in some sense, there's a choice about what part that is. Indeed, insofar as we view ourselves as having free will and choosing freely what observations to make, and perhaps what our own structure should be, we are in control of that choice. Our basic nature as observers will nevertheless determine some of what we experience, most notably core laws of physics, but beyond that, it's our choices as observers that effectively determine which possible program we're running in the Ruliad. So if we think of such programs as simulations running on the Ruliad, then it's not as if there's some outside entity that's picking the programs. It's our nature and our choices that are doing it. Mathematical reality. We've talked a lot about what there ultimately is in the concrete physical world, but what about the abstract mathematical world? One of the surprising things about the Ruliad is that it implies a remarkably close connection between the ultimate foundations of physics and of mathematics. In our physics project, we had to start by inventing a machine code level representation of the physical world in terms of hypergraphs, rewriting rules, and so on. In mathematics, it turns out that there's already a well-established machine code level representation. Networks of theorems stated as symbolic expressions and transformed into each other according to essentially structural laws of inference. At this level of description, any particular field of mathematics can be thought of as starting from certain axioms, then building up a whole multiway graph of all possible theorems they imply. The paths in this graph correspond to proofs, with the phenomenon of undecidability manifesting itself in the presence of arbitrarily long paths, and the theorems that human mathematicians find interesting are dotted around the graph. So what happens if instead of looking at a single axiom system, we look at all possible axiom systems? What we'll get is a structure corresponding to the entangled limit of all possible proofs, based on rules derived from all possible axiom systems. But we've seen an equivalent structure before. It's just the Ruliad. But now, instead of interpreting Emes as atoms of space, we interpret them as atoms of mathematics. or the lowest level elements of mathematical expressions. And instead of interpreting slices of the Ruliad as corresponding in the limit to physical space, we interpret them as defining metamathematical space. So in addition to encapsulating all possible computational processes, the Ruliad also encapsulates all possible mathematical ones. But how do human mathematicians, or what we can call mathematical observers, perceive this? How do they extract what they consider meaningful mathematics? Physical observers get their view of the world, in essence, by building up a thread of experience through time. Mathematical observers get their view of the world by starting with some set of theorems or axioms that they choose to assume, then moving outwards to build up a larger collection of mathematical results. The raw Ruliad is full of computational irreducibility, but in both physics and mathematics, the goal is in effect to find pockets of reducibility that let observers like us get summaries that we can fit in our finite minds. In physics, this manifests in identifying concepts like space and then identifying laws that must hold about them. So what is the analog for mathematics? In principle, one could operate at the level of axioms or even below, but in doing Euclidean geometry, for example, it's perfectly reasonable to talk in terms of the Pythagorean theorem without always going down to the lowest level of definition, say for real numbers. It's very much like in physics, where for many purposes one can talk about something like the flow of a fluid without having to worry about what's going on at the level of molecular dynamics. And indeed, just like in physics, the fact that mathematics is done by observers like us has immediate implications for what mathematics is like, or in effect, for the laws of mathematics. What are these laws? The most important is that higher level mathematics is possible. In other words, that mathematicians can in fact successfully do mathematics at the fluid dynamics level without always having to drop down to the raw molecular dynamics level of axioms and below. There are other laws of mathematics one can expect. For example, the homogeneity of mathematical space implied by the structure of the Ruliad has the consequence that pure metamathematical motion should be possible, so that there must be dualities that allow one to translate from one field of mathematics to another. As another example, there should be analogues of general relativity in metamathematical space, with the analogue of black holes in which time stops, being decidable mathematical theories in which proofs always stop, in the sense that they're a bounded length. But just like for physics, we're in a sense getting from the Ruliad the mathematics we get because we are observers of the kind we are. We might have imagined that we could just invent whatever mathematics we want just by setting up an appropriate axiom system. But the point is that only some axiom systems, or in effect some slices of the Ruliad, will allow observers with our characteristics to coherently do mathematics. Our everyday experience of the physical world gives us the impression that we have a kind of direct access to many of the foundational features of physics, like the existence of space and the phenomenon of motion. But our physics project implies that these are not concepts that are in any sense intrinsically there. They're just things that emerge from the raw Ruliad when you parse it in the kind of ways physical observers like us do. In mathematics, it's less obvious, at least to anyone except perhaps experienced pure mathematicians, that there's direct access to anything. But in our view of mathematics here, it's ultimately just like physics, and ultimately also rooted in the Ruliad, but sampled not by physical observers, but by mathematical ones. So from this point of view, there's just as much that's real underneath mathematics as there is underneath physics. The mathematics is sampled slightly differently, but we should not in any sense consider it fundamentally more abstract. When we think of ourselves as entities within the Ruliad, we can build up what we might consider a fully abstract description of how we get our experience of physics. And we can basically do the same for mathematics. So if we take the common sense point of view that the physical world exists for real, we're forced into the same point of view for mathematics. In other words, if we say that the physical world exists, so must we also say that in some fundamental sense, mathematics also exists. Underneath mathematics, just like underneath physics, is the Ruliad. And so in a sense, what is ultimately there in mathematics is the same as what is ultimately there in physics. Mathematics is not something we humans just make. It's something that comes from the Ruliad through our particular way of observing it, defined by our particular characteristics as observers. Observers in the vastness of the Ruliad. One of the things we've learnt over the past few centuries is just how small we are compared to the universe. But now we realize that compared to the whole Ruliad, we're still even vastly much smaller. We're certainly not as small as we might be, though, and indeed at some level we're actually quite large, being composed not just of a few atoms of space, or for that matter, Emes, but an immense number. We are in effect intermediate in scale, huge compared to Emes, but tiny compared to the whole Ruliad. And the fact that we as observers are at this scale is crucial to how we experience the universe and the Ruliad. We're large enough that we can in some sense persistently exist and form solid, persistent experiences, not subject to constantly changing microscopic details, yet we're small enough that we can exist as coherent, independent entities in the Ruliad. We're large enough that we can have a certain amount of inner life, yet we're small enough that there's also plenty of external stimuli impinging on us from elsewhere in the Ruliad. We're also large enough that we can typically think in terms of continuous space, not atoms of space, and we can think in terms of continuous quantum amplitudes, not discrete multiway threads. But we're small enough that we can have a consistent view of where we are in physical space and in branchial space. And all of us human observers are tightly enough packed in physical and branchial space that we can basically agree about what's happening around us, and this forms the basis for what we consider to be objective reality. And it's the same basic story when we think about the whole Ruliad, but now where we are determines in effect what rules we attribute to the universe, and our scale is what makes those rules both fairly consistent and fairly definite. Some features of the universe, like the basic phenomena of general relativity and quantum mechanics, depend only on our general characteristics as observers, but others, likely like the masses of particles, depend on our place in the Ruliad. And for example, we already know from traditional physics that something like the perceived mass of an electron depends on the momentum we use to probe it. When we ask what there ultimately is, one of the most striking things is how much there ultimately is. We don't yet know the scale of discreteness of space, but conceivably it's around 10 to the minus 80 meters, 90 meters, implying that at any given moment there might be 10 to the 400 atoms of space in the universe and about 10 to the 500 in the history of the universe so far. What about the whole Ruliad? The number of Emes is exponentially larger, conceivably of the order of 10 to the 500 to the power 10 to the 500. It's a huge number. But the fact that we can even guess at it gives us a sense that we can begin to think concretely about what there ultimately is. So how does this all relate to human scales? We know that the universe is about 10 to the 80th times larger in volume than a human in physical space. And within one human at any given time, there might be 10 to the 300 atoms of space. Our existence throughout our lives might be defined by perhaps 10 to the 400 Emes. We can also guess at our extent in branchial space and in the whole Ruliad. There are huge numbers involved that give us a sense of why we observe so much that seems so definite in the universe. In effect, it's that we're big enough that our average perceptions are very precise, yet we're small enough that we're essentially at a precise location within the Ruliad. A remarkable feature of thinking in terms of Emes and the Ruliad is that we can do things like compare the sizes of human-scale physics and mathematics. And a rough estimate might be that all the mathematics done in human history has involved perhaps 10 to the 100 Emes, vastly less than the number of Emes involved in our physical existence. We can think of our big but small scale as being what allows us to be observers who can be treated as persistent in time. And it's very much the same story for persistence in space. For us to be capable of pure motion where we move from one place to another and are still persistently ourselves, we have to be large enough, large compared to the scale of Emes, and tiny compared to the scale of the Ruliad. When it comes to moving the physical universe, we know that to actually move ourselves, say with a spacecraft, takes time. But to imagine what it's like to have moved is something that can be done abstractly and quickly. And it's the same at the level of the Ruliad. To move ourselves in the Ruliad, in effect, requires an explicit computational translation from one set of rules to another, which takes typically irreducible computational effort and therefore time. But we can still just abstractly jump anywhere we want in the Ruliad. And that is, in effect, what we do in Ruliology, studying rules that we can, for example, just pick at random or find by enumeration. We can discover all sorts of interesting things that way, but in a sense, they're at least at first alien things, not immediately connected to anything familiar to us from our normal location in the Ruliad. We see something similar in mathematics. We can start enumerating a huge network of possible theorems, but unless we can find a way to transport ourselves as mathematical observers more or less wholesale in metamathematical space, we won't be able to contextualize most of those theorems. They'll seem alien to us. It's not easy to get an intuition for the alien things out there in the Ruliad. One approach is to use generative AI, say to make pictures, and to ask what happens if the parameters of the AI are changed, in effect moving to different rules and a different part of the Ruliad. Sometimes one gets recognizable pictures that are described by some concept, say associated with a word in human language, but in the vast majority of cases, in the vast majority of cases, one finds oneself in interconcept space, in a place for which no existing human concept has yet been invented. And indeed, in experiments with practical neural nets, the fraction of this tiny corner of the Ruliad spanned by our familiar concepts can easily be just 10 to the minus 400 of the 10 to the minus 600 of the total. In other words, what we have ways to describe, say in human language, represents an absolutely tiny fraction of what there ultimately is. But what happens if we invent more concepts? In some sense, we then grow in Rulial space, so that we as observers span a larger part of the Ruliad. And perhaps we might see it as some kind of ultimate goal for science and for knowledge to expand ourselves throughout the Ruliad. But there's a catch. The fact that we can view ourselves as definite individual observers depends on us being small compared to the Ruliad. If we could expand to fill the Ruliad, we would in some sense be everything, but we would also be nothing, and we would no longer exist as coherent entities. Developing a science of metaphysics. Metaphysics has historically been viewed as a branch of philosophy, but what I've argued here is that with our new results and new insights from science, we can start to discuss metaphysics not just as philosophy, but also as science, and we can begin to tell an actual scientific story of what there ultimately is and how we fit into it. Metaphysics in the past has basically always had to be built purely on arguments made with words, and indeed perhaps this is why it's often been considered somewhat slippery and fragile. But now with the kinds of things we've talked about here, we're beginning to have what we need to set up a solid formal structure for metaphysics, in which we can progressively build a rich tower of definite conclusions. Some of what there is to say relates to the Ruliad, and is in a sense purely abstract and inevitable, but other parts relate to the subjective experience of observers, and for us, basically human observers. So does metaphysics somehow need to involve itself with all the details of biology, or for that matter, psychology? The big surprise is that it doesn't, because the science says that knowing only very coarse things about observers, like that they are computationally bounded, already makes it possible to come to precise conclusions about certain features and laws they must perceive. There is, in effect, an emergent metaphysics. The Ruliad provides a form of answer to what there abstractly ultimately is, but to connect it to what for us there really is, we need to know the essence of what we are like. Investigating features of the Ruliad is a lot about doing pure Ruliology and empirically studying what abstract simple programs do. Talking about observers is much more an exercise in meta-modeling and taking largely known models of the world and trying to extract from them the abstract essence of what's going on. To make a science of metaphysics somehow requires both of these. But the exciting thing is that building on the computational paradigm and intuition from studying the computational universe, we're getting to the point where we can begin to give definite answers to questions of metaphysics that for millennia have seemed like things about which we could just make arguments, but never come to conclusions. Unlike so many other branches of philosophy before it, metaphysics now seems destined to make the transition from being a matter purely of philosophy to being one of science, finally giving us answers to the age-old question of what there ultimately is. And that's what I had to say about these questions. Let's see, we have a whole bunch of comments here, and let me see if I can parse some of them out. Stuart is asking, or saying, what is ontologically real is determined by the scale of the Markovian observer. I'm not sure I fully understand all of those words, but I would tend to agree that what we can consider real, sort of what we can consider to be our objective reality, is determined in part by our scale with respect to the Ruliad. I think that's a correct statement. So Don asks, if all rule sets are running simultaneously, is there any randomness there? For example, are all irrationals being generated? Are there random mutations? If yes, it seems order would exist in a sea of randomness. So yes, the idea is that all rule sets are being run simultaneously. There is no randomness. That all the structure of the Ruliad is a completely determined thing. It is like saying, is there randomness in the structure of all the theorems of arithmetic? You start from the axioms, let's say, of piano arithmetic, you derive all possible theorems of arithmetic. The thing you derive is a completely determined thing. Now, the question of, for the physical universe, for example, of what we perceive in the physical universe, that depends on where we are in the physical universe. Let me give an analogy. The question, we can say, is it random? How do we determine what the night sky is like? Well, depends what planet we're on. It depends what galaxy we're in. There is a definite answer to that. At any planet in any galaxy, there is a definite night sky. But assuming that the planet isn't somehow embedded in some combination of stars that keeps it light all day, or all the time. But in any case, there is some definite answer to what is the appearance of the night sky. But that answer is determined by where you happen to be, what planet you happen to be on. It's not, and it's the same kind of thing with what we perceive to be going on in physics. There is a definite, the Ruliad is definite, but where we are in the Ruliad is something that is not theoretically determined. It's something where we are where we happen to be, so to speak. We are where we are. That's not something about which there's a theory about we have to be here. Now, there may be things we can say about where we happen to be. We're probably on a solid planet. If we're observers with detailed characteristics like us, we're not in the middle of a star or in the middle of intergalactic space or something like this. There are things we can say, but there's a lot we can't say just on the basis of kind of an ultimate theory. It is just we are where we are because that's where we are, so to speak. Let's see, Don has another question. Since space appears to be nothing, at least non-relativistically, wouldn't this suggest something is cancelling to create this apparent zero? Oh, space isn't nothing. In existing theories of physics, traditional theories of physics, in quantum field theory, space is full of all sorts of stuff. Every quantum field has, every mode of every quantum field has a certain degree of activity in the vacuum, in what is otherwise thought of as space. In our models, the way that works is space is formed from all of this activity in this hypergraph. That is what makes space. Now, that's always there. So for us, we just say, well, what's happening relative to the space we know is always there? That's our sort of zero of activity, is the space that's always there. Now, that zero of activity can be deformed by the presence of densities of energy and so on. That leads to gravity, things like that. But even in traditional physics, space is a very active place. Space is full of lots of quantum fluctuations. lots of 0 point activity, and so on. It's very dynamic. Those kinds of things in our models, we get to see underneath all of that. In quantum field theory, we're talking about things in terms of modes of quantum fields, or ultimately things about particles like electrons and photons and so on. What we're talking about in our models of physics is something unbelievably much smaller than that. It's the raw material from which an electron is a big thing that's made from it, and a black hole similarly. And probably there's a close relation between black holes and electrons, but they're all just made of these elements that form that we can talk about as forming the structure of space. So we're saying that sort of what's always there is all of this activity. Without activity, the different parts of space would not be knitted together. There would not be a coherent thing we can think of as space. There would be one set of events happening here, another set of events happening here. There'd be no relation between them. If it wasn't for all those events in the middle, so to speak, we wouldn't be able to say there's this thing that is a coherent kind of slab of space at a certain moment of time. So now you can ask questions about, well, what does that sort of background of activity in space, what does that lead to? In traditional physics, one of the big kludges has to do with the origin of mass. What is natural, both in traditional physics and in our models, is that everything is massless, which means everything goes at the speed of light, like a photon. But things actually don't all go at the speed of light. Like we as observers hang out with mass, not at the speed of light. If we went at the speed of light, for example, we would have no notion of time. The photons that an observer of the cosmic microwave background observes today, as far as they're concerned, the universe just started and then they got absorbed. There's no time has passed for that, for the photons. And it is the presence of mass for observers like us that leads to the possibility of our perception of the passage of time. And what leads to mass? In traditional physics, there's this big kludge that's called the Higgs mechanism, which has the idea that throughout space, there is a certain amount, a certain intensity of this Higgs field, and every particle kind of is affected by, is coupled to that with a certain coupling constant. And that coupling constant, the amount of coupling to that Higgs field, is what determines the mass of the particle. What it's saying is particles are sort of just going through the vacuum, except there's Higgs field in the vacuum. It's not just nothing there. And those particles are continually interacting with this Higgs field. And it's that continual interaction, absorption, emission, et cetera, et cetera, et cetera, that leads those particles to not be going at the speed of light. Just like when you have something like light going through a piece of glass, it doesn't go through the piece of glass at the speed of light because it's continually getting absorbed and re-emitted by atoms. It's more or less the same thing with the Higgs field. There's continual interaction with that leads to that causes the particles to not sort of always have to go at the speed of light and to behave as if they have mass. In our models, there's a sort of lower level version of that. We don't fully understand it yet, which I think is going to show us sort of the origin of mass, and it's going to tell us that sort of there are collective effects that correspond to Higgs particles, but the true story will be something at a much lower level. Now, we can ask all of this activity that's happening at this microscopic scale that is the structure of the vacuum of space, the thing that forms space. What can we say about it? Well, in traditional physics, there's been a problem because all of that activity in quantum field theory leads to a very high energy density in space. In fact, so high an energy density that it leads to so much gravity that the universe will be curled up into a tiny ball. And that's always been a bit mysterious why that doesn't happen. In our models, the reason that doesn't happen is because the thing that's making the structure of space and that's leading to all that activity that we can interpret as energy, that's the same thing as actually makes space. And it's the same thing as what makes gravity and so on. So you don't have this phenomenon of one thing is sort of making the space, another thing is putting energy into the space, and then that energy is having an effect on the space and so on. Now, I think there are questions about what macroscopic manifestations might there be of all of this microscopic activity in the structure of space? And could it be the case that different places in the universe are sort of spaces acting different in different places in the universe? My guess is that there is. And actually, there's sort of an analogy in the history of science, which is the question of people wondering sort of if you know that matter is microscopically made of molecules, what macroscopic manifestation does the microscopic structure of matter in terms of molecules have? Well, the big answer is heat. Heat is the consequence of the microscopic motion of molecules in matter. But it is a macroscopic phenomenon that we can perceive macroscopically, even though it is a consequence of the effect of microscopic molecules of matter. And so my guess is that there are similarly effects, macroscopic effects of the microscopic structure of space. My leading contender is that dark matter is kind of the analog of that is the macroscopic manifestation of the microscopic structure of space, as heat is the macroscopic manifestation of the microscopic structure of matter. Let's see, there's a question here from Prab. So is math discovered or invented? Well, it's somewhere in between, because what's ultimately there, all possible math, is the Ruliad. It's a thing that's just there to be explored, to be discovered. But the question of which parts of the Ruliad we sample is a matter of what we choose to do and how we are as mathematical observers. So in a sense, there is an all possible math that's there, but the math that we choose to do is something that is kind of invented by the ways that we choose to do it, so to speak. Now, I think there is some inevitability to the kind of math that we can choose to do. In other words, there is math where no human observer with a finite mind could sort of keep track of all the things that are going on. There's math where inevitably you're kind of drowning in undecidability. You're drowning in computational irreducibility. Nothing hangs together. There are no general things you can say in math. We could be sort of unlucky and pick a direction in the Ruliad, a set of axioms for mathematics where everything just shreds itself. There are no global things to say about math. Everything is a detail. Everything is a proof that we can't do from those axioms and we have to add more and so on. The fact that we have chosen certain branches of mathematics, geometry, algebra, arithmetic, whatever, those are things that turn out to be things that mathematical observers like us can sort of exist in, can exist we can exist without being shredded, so to speak. We can exist without it being the case that the conclusions we make lead us to be sort of forced down to the lowest level of Emes and the Ruliad and all its details, that we can operate at sort of the fluid dynamics level without having to go down to the molecular dynamics level. Now, it's long been wondered in mathematics whether there are constraints on what possible axioms in mathematics could be. I mean, the axioms of arithmetic seem sort of natural to make, given that we have our intuitive notion of numbers. The axioms of set theory and of infinite sets are much less obviously intuitive to make. It's much less obvious whether certain axioms should be assumed or not, because we don't really have good intuition about infinite sets and transfinite induction and all these kinds of things. And so, for example, the continuum hypothesis is one example of something where it's been very unclear whether there is a definite answer to how the continuum hypothesis works. We know it's independent of the other axioms of set theory. But the question is there a humanly reasonable decision about is the continuum hypothesis true or not? Or is it something that we could truly arbitrarily choose? My guess is that for human mathematical observers to operate without sort of being shredded and with sort of finite mathematical minds, that there is a definite answer to the continuum hypothesis. There's only one possible decision about how it can go that leads us to sort of maintain ourselves as coherent mathematical observers. So it's I don't know whether you say things are discovered or invented, but it's an interesting kind of, that question, as is so often the case, the true answer is something I think that is neither on one side nor the other, but something quite unexpected that kind of weaves those two ideas together. Constantine asks, do you think that metaphysics could ever become purely a matter of science, or will it always be part philosophy? I think that the question of what an observer can be like is something that, in some sense, is something arbitrary, is something that you can debate, because we're observers of the kind we are built by biology. We can make AIs that are observers of a slightly different kind. We can imagine the weather and we can say, is it an observer? Is it an observer that is, we can always discuss that. And I think as kind of we end up being different from the way we are. We have different senses as a result of technology giving us sensors to observe different things about the universe. Maybe we have different ways that we can actually operate in our brains. Maybe we can end up not with a single thread of experience. Maybe if we have sort of the neural coprocessor that allows us to have other threads of thought at the same time as we are having our main thread of experience, there are things like that that will lead us to a very different set of conclusions about metaphysics as it's relevant to us. And I don't think those kinds of things, we can make scientific conclusions about each of those, but what direction we go in is certainly going to be something that is a sort of funny matter of, I don't know whether it's a matter of the arc of history or a matter of of choice of what we choose to be like, or how that works. What usually makes things scientific, or more than that, technological, is when we have certain human purposes that we want to achieve, and we're trying to build a tower for the purpose of achieving those human purposes. And it's a reasonable question. What can we conclude from a kind of computational metaphysics, for example? What are sort of the conclusions? What are the scientific, what's the technology we want to build on top of that? I suppose one perhaps interesting thing to say would be kind of, there have been sort of levels of metaphysics that have happened as a result of science in the past. I mean, a notable one is sort of the Copernican transition. Before that time, there was kind of an assumption that the way we intuitively perceive things must be basically the way things are. We're standing still on the Earth. The Earth can't be moving around the sun. It just has to be here standing still, because that's what we intuitively perceive. Then what became clear is that what is abstractly, mathematically discussable is what we can at some level think of as the true reality of what's there, more so than our senses and our intuitive sense that we are standing still right here. So in a sense, the Copernican revolution, the Copernican transition, was one to an idea that what's ultimately there can be described sort of in abstract terms in terms of mathematics and so on. I think the kinds of things we're learning from the science that I'm talking about in its relationship to metaphysics is that we're getting increasing evidence that we can think of things as being sort of computational all the way down. And that's kind of like the transition that happened where we went from everything is just the way common sense says it is, to things have to be derived in some formal way in terms of mathematics. Now we're talking about things can be sort of derived in some formal way computationally. And I suppose, if we're starting to ask what are the sort of what are the implications of this for sort of the way we do things, as soon as we realize that things are computational all the way down, it kind of justifies us thinking about everything about our lives and what we do, and the sort of ethics of what we might do and so on, of applying computational ideas to all of those kinds of things. It makes sense to do that, given that we know that, or we seem to be discovering that the universe is in some sense fundamentally computational all the way down. But I don't know. See, what tends to happen when things turn into sciences is you can build big towers based on them. It's more true in the exact sciences than in the more descriptive sciences, more true in physics than in biology. But once you have sort of a formalized version of things, you can start building a big tower. And the question is, where does the tower lead? And in physics, it's led, among other things, to lots of technology. In biology, we haven't been able to build such a good tower because we hadn't really had a theory of biology. I've been working on that a bunch in recent times, and we're making really kind of interesting progress. But we haven't had that same kind of towering ability, so to speak. So now, if we can inject more science into metaphysics, what is the tower that we could build on metaphysics? What is the tower that we could build on knowing things about what there ultimately is and so on? I'm not sure. I don't know. I think that that's always it's a very difficult thing to imagine the towers that get built. For example, if we go back to antiquity, when Aristotle was sort of analyzing arguments and deducing syllogistic logic, that was that for a couple of millennia, one was just saying there are certain patterns of arguments in logic. And then along came Boole, who gave a sort of more formalized version of how you could think about those kinds of things. Then you wait another 100 years and you get to the idea of computation. And on top of what was originally, syllogistic logic and the structure of human arguments came the sort of formalization of Boolean algebra. And then on top of that came, in some sense, the idea and operation of computers and this whole notion of computation. The fact that that got built on this kind of on this kind of conceptual foundation is a remarkable thing. And the things that we can now think about and do with computers and now thinking about sort of the computational paradigm are really hard to imagine, at least as far as I'm concerned, from sort of the origins of Aristotelian logic and so on. I mean, I would say that I have a very practical version of this that I'm experiencing right now. We're building this thing we're calling symbolic discourse language, which is an attempt to really sort of have a formal computational representation of everyday statements in the world. We've done that pretty well for lots of objective statements that we represent in Wolfram language. We can represent things about countries and chemicals and mathematical algorithms and all those kinds of things. We're trying to represent things like I'm going to I want to drink some water now. We're trying to represent those kinds of things in a formal way. I fully think that what we're doing is kind of generalizing the notion of kind of things like logic from something that is just about, propositions that you make to things that something that has a lot more structure about the way things are and the fact that there are observers and entities in the world and so on. And I don't know. Once we built our symbolic discourse language, yes, I know it will be a good foundation for LLMs and it'll have all sorts of interesting things to say about computational law and all kinds of things like this. But what is the tower that one can build from that? I don't know. It's an interesting thing to think about. It's like imagine the tower that could be built from Aristotelian logic 2,000 years later. It's hard to imagine. I think that so in any case, I think the so I don't know what sort of what the scientific tower that could be built on a scientific metaphysics or beyond that a technological tower might be like. Okay, more from Constantine. Can there be such a thing as pure science? That is, science which does not rely on any philosophical assumptions concerning the nature of observation. Boy, these are not easy questions. What is science? I think of science as being the attempt to take what there is and make a human narrative out of it. I mean, science is something done by humans. It's something where you're attempting to make a bridge from what is to what we can sort of have a narrative about in our minds, I think. And so the question you might ask is there a pure science independent of the carrier of narrative? That seems like a reasonable question. Is there, in some sense, a way of, I mean, in my definition of science, that science is this bridge from what is to kind of a narrative in a mind like ours, then I think one's saying that that bridge makes no sense if there's no destination mind, if there's no destination observer into which to connect that bridge. I think that's what I would have to say in that sort of, but it's a little bit depends on the meaning of the the concept of science. But I think that's a reasonable practical meaning to science, the thing that bridges from what is to a narrative that our minds can deal with. Okay, Constantine again. Um, Philosophers such as Kant, Wittgenstein, and Kripke understand rules to be imperatives that can be followed or violated, understood or misunderstood. Do you think that this also applies to the computational rules of the Ruliad? Are they immune from such deviations? Well, I think that what we're saying is that the Ruliad is simply following these abstract rules. Now, I don't know. See, this is where you hit the edges of my knowledge, because uh, I I like to do my homework in every field that I am involved in. Philosophy is uh, it's too deep a rabbit hole for me to have penetrated properly into it, and I think that uh, my my knowledge of sort of historical uh, results, claims, conclusions in philosophy is is not as great as I would like it to be. And that's not in recent times I've put some effort into learning these things, but I always find it very difficult. When you're learning about something like the history of science, there's a certain amount of who, what, when, where, of definite things happened, so and so discovered this definite thing, and it's sort of a thing you can talk about. When it comes to, what did Kant say about such and such, that's so much more difficult for me to have a definite conclusion about. I did my homework. I bought the collected works of Immanuel Kant. They fill a whole shelf in my library. Um, but what exactly does all that mean is very hard for me to say. But I think the question that's being asked here is um, that there's a notion perhaps that rules are sort of imperatives followed or violated. That's certainly what we think about, for example, things like human laws. We say, the law says this, but somebody can choose to break the law. Well, we think of the laws of nature as being something that we can't break. That's just nature does what it does, and its laws are inviolable. So we've thought. It's a little trickier in my view of how things work. The Ruliad has all is the Ruliad is just following what it follows. It is as inevitably following what it follows as some formal mathematical system does what it does. You can't break the law that 1 + 1 = 2. If you've defined one and plus and equals and so on, you can't break that law. It makes no sense to do that. It's something where it just has that structure. Now, okay, you could recurse down and say, what about the laws of inference that you're using to conclude one thing from another? I think that in the way I'm thinking about things, that that there at some level it is just there is a specification of what happens, and that's what we're saying is this abstract thing follows that specification. And you could say, well, it might not have to. Okay, it might be a different abstract thing, but this abstract thing follows the specification. So then the question is, you've got these underlying specifications. They're just followed, no choice, because they're just specifications of a thing, and you have that thing. That thing is the Ruliad. You've got the specification of the Ruliad. The Ruliad is that thing. So now we say, well, are the laws of nature that we perceive, are they inevitable? Are they sort of inviolable? Well, that gets a little trickier, because what I've been talking about is that the laws of nature as we perceive them are things that are our sampling of the Ruliad based on the way we are as observers. So let me give you an example. The second law of thermodynamics. So people have been talking about, well, the second law seems to be true. People have been very confused about how you would prove the second law. When it was first invented in the 19th century, people said, we're going to take mechanics and we're going to prove the second law. Then people got confused about that. They started saying, well, maybe radiant heat and so on will prove the second law. Maybe there are other sort of external physical phenomena that will prove the second law. None of that really worked out. By the beginning of the 20th century, people had sort of been like, well, I think the second law was proved a few decades ago. We don't have to worry about it anymore. And that was the situation for about a century. I myself have been interested in the second law for more than 50 years now. And I think I finally understand from all of these ideas about computational irreducibility and so on, why the second law is true for observers like us. The second law isn't generally true. The second law is only true for observers who are computationally bounded. It isn't true for arbitrary observers. Now, having said the second law is true, and people say, rather various wags at various times have sort of described the second law as being sort of a most fundamental fact about the universe that couldn't possibly be any other way. I think they're wrong about that. And they're wrong about it because the second law only is the way it is because we are observers of the kind we are. And so it's kind of funny when you hear that the second law is an inevitable proven law of physics, that practically every week in the leading physics journals, there are articles about so-called Maxwell's demons and other things that violate the second law. How could that possibly be? Well, the answer is that those things are violating the second law for observers not like us. They're doing things that happen at the level of individual molecules and things like this that are inappropriate for observers like us who don't get to mess around with individual molecules unless we're using big stacks of technology and so on to observe those individual molecules. So for observers not like us, the second law is regularly violated. But for observers like us, the second law has to be the way it is. So in some sense, the violation to say that a law is a thing that has to be followed is to say that what I'm saying is it can be the case that a law has to be followed for observers like us. But if you deviate from being an observer like us, then all bets are off and the law can be violated, so to speak. So anyway, a few thoughts about that. Sam is asking, what is the computational metaphysics research program? Are they, I suppose that means us, me, and so on, doing simulations, and if so, of what? Well, it's an interesting question. We were lucky enough to get a little grant for doing philosophy, and I think we may get some other contributions to our philosophy efforts at our Wolfram Institute. It's a funny thing. I've been running technology organizations for a long time, my current company for 40 years this year. And I'm kind of familiar with the idea of how you make innovation happen, how you deliver products in a technology company. I think I got that after doing it for whatever it is, nearly 48 years or something now. How do you do basic science? Well, I've been doing that myself. People have been helping me with that. I think I have some understanding now of how to have sort of an arc of progress in basic science. What about philosophy? How does one run a philosophy project? That's an interesting question. I mean, I can reflect on something in my own distant past history. My mother was a philosophy professor in Oxford, and one of the things that I always said when I was a kid is if there's one thing I'll never do when it's grown up, it's be a philosopher. Okay, so I'm landing up in a philosophy live stream here, so that's a bit embarrassing. But be that as it may, my argument for why it never made sense, I would never consider doing philosophy, is look, there just isn't any progress made. You guys are still arguing about the same things you were arguing about 2,000 years ago. So the question is, what I'm used to in technology is make things, deliver things, distribute them to the world, make the next thing that builds on the thing you just built and so on. In science, I have some understanding of sort of the flow of how to do things. In philosophy, it's less clear, to me at least. One thing that I know is the case is that, the things we figured out connect to lots of things that have been said by philosophers in the last couple of thousand years. I want to understand those connections. I think that's very useful to do that because I think In some cases, there are things where people have refined the question over the course of hundreds of years. The question has been refined, perhaps better refined than I've been able to refine it. And now we've got a methodology to say this refined question, which we can get from the history of philosophy, we can now have something to say about. I also think that there may very well be, for example, one of the things I'd really like to see is what can we say about observers like us? And I think there are characterizations that may have arisen in philosophy that will help us to understand what it is that we can really say about observers like us. For example, one big prize, as far as I'm concerned, is knowing why we perceive the universe as having three dimensions of space, more or less. My strong guess is that when we finally figure this out, we'll be like, we'll feel like idiots because it'll be some feature of us as observers that we completely take for granted that kind of reaches in from behind and forces us to parse the world as three-dimensional. And I think we may get that from philosophy. Now, one of the things that is, of course, the raw material from my efforts in computational metaphysics and so on is simulations of things, is ruleology, the study of simple rules and what they do. I mean, insofar as I've managed to get anywhere with this, it's because I've spent decades just looking at what's out there in the computational universe and seeing what happens and having my intuition regularly exploded by what I actually observe. And I think some of the things we're doing right now in biology probably are the things which are closest to sort of addressing kind of the simulations of computational metaphysics. Things like, is it inevitable that there will be self-replicating things in a system? And perhaps things about, is it inevitable that there will be observer-like things in a system and so on? I think that's how we potentially get to do kind of, grinding lots of computer time studying metaphysics, so to speak. But I still don't fully know how that's all going to come together. But I feel like we're making progress in doing that. Let me give you an example of something, a project I'm working on right now. It's about the theory of bugs. And I was talking to a team earlier today, and they're so used to me working on the most bizarre things that I'm talking about this. And they're like, do you mean software bugs or do you mean entomological bugs? Because it wasn't so obvious, because I might be thinking about either one of those, but I mean software bugs in this case. And it's sort of interesting because if you have a rule by which something's supposed to operate in it, there's an underlying rule by which it operates. There's kind of a thing you can describe about what it does. And that thing you can describe about what it does is kind of like a law of nature that you deduce from sort of high above the underlying Ruliad, which is the underlying laws of some Turing machine or something like this. High above that is the statement, this Turing machine always computes the function 2n plus 3. Okay? But then occasionally, maybe it doesn't. So that's a little bit like a miracle in the natural world. It's like usually it works like this. And we've tried to reverse engineer. We might have tried to reverse engineer what are the underlying rules, but we have observed these rules and we've applied scientific induction. So this is always how things are going to work. But now, occasionally, maybe there's a bug. In other words, it's kind of like in the universe, it's kind of like the Matrix movie. Every so often there's something about the universe that doesn't seem to quite fit. It's like a bug in the universe. Now, of course, in the picture of the universe being something that emerges from this underlying computational rule, there are no bugs. Everything is a feature. Everything just does what it does in the universe. But nevertheless, from the point of view of laws that we might have deduced, there can be bugs, because our law might say it's not going to work that way. The Turing machine is always going to compute 2n plus 3. If for n equals 10,000, it doesn't compute that, that's a bug. So but studying that and trying to get an intuition for kind of how there can be bugs is kind of like, it gives one, I think, it gives one sort of an angle on thinking about some of these questions about scientific induction and the validity of scientific induction. I think that the ability to do scientific induction, why does scientific induction work? I think it works because of our scale relative to the Ruliad and so on. The fact that it could be the case that everything is unpredictable. And there's nothing you can say, nothing you can deduce from having seen it before that you'll see it again, and so on. Franz is asking, what is your own current best take on how the idea of the Ruliad could turn out to be wrong? It's a reasonable question. Could mathematics turn out to be wrong? How would we answer that question? Could calculus turn out to be wrong? The fact is, these things are formal structures, and the way in which calculus can't turn out to be wrong, calculus can turn out to be irrelevant to the world that we're in or the kinds of questions we want to ask, but it can't really be wrong. And I think it's the same story with the Ruliad. It could be the case that the things we want to answer about nature, about why the universe is the way it is, that it's a formalism, but it's a formalism that just isn't the right formalism for addressing the kinds of things we want to address. I mean, in some sense, I could already say, if somebody wants to know, predict the weather tomorrow, the Ruliad is not the right place to start. The Ruliad is so far below the weather that it's not, it's wrong in that sense. In the same sense that calculus is wrong as a way to figure out, well, let's say some aspect of psychology or something. Probably calculus is not the right theory for that. It's not the right formal structure for talking about that. So in that sense, it can be wrong. I don't think it can be wrong in the sense that it is a formal structure that is the way it is. Let's see. Constantine. You introduced the helpful concept of an Emes as an individual atom of existence, which everything in the Ruliad is comprised of. Emes sound similar to Leibniz's monads, which are indivisible, non-physical building blocks of all reality. According to Leibniz's monadology, the universe is accordingly comprised of just one element. Do you share this monism, according to which even space, time, and matter are all ultimately illusions, or do you think he goes too far? Okay, there's, again, you're pushing me into history of philosophy, which I consider myself naive about. But I think one of the key things Leibniz didn't know is that you can get soul from non-soul. You can get sort of richness from non-richness. People didn't know, frankly, until things I figured out in the 1980s, that you could go from simple underlying rules for things to sort of arbitrary richness of behavior. That's not an obvious thing. You might have imagined that insofar as a soul is something like some complicated sort of computational process that's going on, some complicated process, you could only get that sort of richness and complexity from breaking off another piece of soul. And I think Leibniz's monads, he tended to think of them as little souls that could make up bigger souls, so to speak. I think one of the things that's a bit different in what I'm talking about is that there is no little soul in the Emes. The Emes is really nothing. It's really, well, not nothing. It's really just an atom of existence. And I don't think Leibniz really had that idea, from what I understand. I think he more had the idea that for him, it was an atom of soul, and that already had to have a lot of structure in it, a lot of capability. That he had that was something where sort of the big capability comes from the capability of the parts, rather than what we're now saying, that there's this kind of computational irreducibility idea that from very little, from really very little, can come a lot. Leibniz, I think, was very into that kind of idea. I know that, in his invention of binary numbers, I don't know whether he invented them or got them from Chinese missionaries or something, but he was very big on the idea that from just one and zero, you can get everything, so to speak. He was very big on from so little you get so much. I don't think his monads were as featureless and small as the ones and zeros. I don't think. I don't know. I've tried reading his works. I find it really difficult to read. They might be easier in Latin, but my knowledge of Latin probably isn't good enough to read them directly there. but it's just really hard for me to understand these things, and I'm very interested to actually talk to folks who spent a long time studying what Leibniz wrote to try to understand those features. I have to say, Leibniz has been a character I've always been a bit curious about. I've always been struck by, Gödel. I think in perhaps in his slightly nuttier aspects, was always saying Leibniz discovered a great truth and it's been suppressed, so to speak. And I did a number of years ago visit the Leibniz archive and flipped through lots and lots of pages of Leibniz's notes, discovered he was pretty bad at arithmetic, for example, and discovered that he did strange drawings of people and things like this in his notes. But I was kind of wondering whether I would find a Turing machine or something, some representation of computation in what Leibniz was doing. I didn't. But I was kind of struck by he had this medal that he wanted somebody to strike for him that was a medal commemorating the invention of binary numbers. And I can't remember the Latin quite, but from ex nihilo, from nothing, just with one, everything can be descended, so to speak. So he was thinking of that in terms of numbers. I think maybe he tried to extend that to sort of everything in existence, but I don't think he made that jump correctly, because I think he didn't understand this phenomenon of computational irreducibility and those kinds of things, which he couldn't have understood because we only understand it from the intuition that we get from actually using computers and things. So at least that's the only way I've been able to get it. I think I was very struck by the fact that Leibniz made this brass calculator. It's in his archive. And I was kind of struck by the fact that in Leibniz's day, Leibniz had seen more or less one or two computers, whereas now there are billions of computers in the world. I kind of realized that in the future, we'll probably think of everything as being made of computers, but that's a different story. But I think that Leibniz just didn't have that kind of intuition because he didn't have the opportunity to run rules automatically, so to speak, and see their consequences. But I tend to think that this idea that you can think of the universe abstractly in terms of just one kind of thing, I do tend to think that's a reasonable thing to do. Now, I have to say, when I think about the Ruliad, one of the things we've learnt from the principle of computational equivalence, from the idea of computational universality and so on, is there are an infinite number of different ways to represent that same thing. It's not the case that there's only one way. It's like, can we talk about a triangle only in one way? Well, we can talk about it in terms of coordinates, in terms of geometry, et cetera, et cetera, et cetera. There's many ways to talk about things. I think that a very economical way to talk about things is in terms of Emes and the Ruliad, that there really is only one kind of a thing fundamentally we have to talk about. But we could perfectly well make a description in terms of the 18 kinds of rules that exist, and this kind works this way and that kind works that way. In the end, it's all of them, but we could distinguish them in some way. We could make a much more complicated story about it, but I don't think we need to. Franz is asking, is the Ruliad an a priori necessary claim regarding the ultimate shape of the pure epistemic process that cannot be avoided if one actually follows through with all the unfolding implications of the initial fact that all there ever was were directly given discernibles, rules, state changes? Or is the Ruliad a claim beyond the pure shape of epistemology, i.e. a claim on the things in themselves, a statement about the fundamental nature of an assumed or inferred or deduced substrate reality? Boy, that's complicated. Okay. Things in themselves is a very Kantian kind of thing to be talking about. Let's see if I can take this apart. I think what you're asking is sort of, the Ruliad is a thing, and I'm describing it in terms of rules and state changes and Emes and things like that. But what is the thing in itself? I think what I have to say, and this is a place where I'd like to connect it more to what's been thought about in philosophy elsewhere. I think what I would say is that I think of the Ruliad as just this thing, and how we describe it, as I was just talking about, how we describe it, there are many ways to describe it. Let's take the number 7. It's a thing in some sense. We can describe it in many ways. We can think about, it's made of counters. It's the result of applying successor functions. It's this, it's that. We can describe it in many ways, but it seems to have some sort of Platonic existence, at least I think of it that way, independent of the way that it's described. Now, I, a philosopher might take apart my claim here, and I invite that process. I'm planning to do a number of live streams talking to philosophers who've studied kind of traditional philosophy. No doubt we can have that discussion there, and somebody may take apart the view that I just espoused, but that would be my initial sort of take, that it's kind of like the number 7, that it has many descriptions, but it just is. It is the number 7 in itself, so to speak, is a thing. I'm not sure what Kant would have had to say about that. I actually would be curious to know what he would say about the nature of numbers in and of themselves, so to speak. So, technical question here from SB. Is Rule 30 reversible in theory? No, Rule 30 doesn't happen to be a reversible rule. There are many rules you can make in cellular automata, other kinds of rules, where both there's a unique successor and a unique predecessor. When we're dealing with multi-way systems, it gets more complicated because there isn't just one successor, there are many successors, many predecessors. It gets more complicated. It gets very related to the phenomenon of causal invariance. I'm not sure in the end how important that is in the interpretation of what goes on in the universe. The Ruliad is inevitably reversible because it contains both every forward rule and every backward rule. But our sample of the Ruliad may not be perfectly reversible. And I think our sample of the Ruliad, what becomes important is only things like that we perceive there to be a definite causal graph of what happens, rather than this sort of microscopic reversibility. Gosh, Just is asking, is metaphysics the singularity of physics? I don't know. I think I don't know how to answer that. Sorry. James is asking, how fast is the Ruliad growing in respect to the hypergraph of our known universe? Oh boy. So there isn't just one hypergraph for our known universe. There is, for an observer with a particular reference frame and a particular place in Rulial space and a particular place in branchial space and so on, yes, there is one reconstructed hypergraph that is a slice of the Ruliad. But there are a very large number of possible such slices, very, very huge number of possible such slices. And in terms of the sort of growth of the Ruliad, from where we are, there are a hugely exponential number, maybe 10 to the 500 to the 10 to the 500, different possible sort of, that's not right, maybe just 10 to the 500, sorry, not the double exponential there, possible sort of next states of our hypergraph. But which one we perceive, we will perceive some definite sort of strand of those states. But there are many that can occur, and they all are part of the Ruliad. And as I was saying, one of the things that's tricky about the Ruliad is it is defined by its underlying rules. So once you have those rules, in some sense, you can just say, well, I know what the whole Ruliad is going to be like. If you actually were running it on a computer, or if you as an observer were trying to explore it, well, that takes a lot of effort and time. But in principle, knowing its underlying structure, you can just say, here's the whole thing. So in some sense, it isn't growing at all. It's all made it's all just made as an abstract thing. In terms of sort of how fast the different threads of history, how many different threads of history there are, it's some absurdly large number. I've tried to make estimates of this. We need to know just one number in our physics project, and then we'll know just a ton of scales for things. But the number we need to know is what is the elementary length? What is the elementary time? Those are related by just by speed of light. What is the discreteness scale of the universe? Once we have that, we can deduce all these other things. We don't know that. In the 19th century, people were damn lucky that molecules were big enough you could see them, basically, see their effects through a microscope. We don't know whether the atoms of space are, in a sense, big enough. They don't have a physical extent in that sense, but the edges in the hypergraph, what is their effective conversion to meters? We don't know whether they're big enough that we can perceive them with experiments we can do now or 100 years in the future or an almost indefinite time in the future. We don't know. I'm sort of hoping that there are experiments that have already been done that will reveal the discreteness of space. Maybe there are macroscopic manifestations of the discreteness of space. Like I was mentioning earlier, dark matter might be such a thing, in which case we'd be able to say, just from what we already know, we'd be able to say, yep, I know what the discreteness scale is. People almost nailed that with thinking about the heat and gases and so on with molecules. But it was only really definitively clear once you could see Brownian motion in a microscope and things like that. Boone is observing that this gets as a software developer, I'm used to complex logic, but the depth of the subject matter is on another level. Yeah, I'm afraid for myself, it's taken me kind of decades to get to the point where I think I can reason about these kinds of things. And a lot of that capability comes from the actual experience of doing computer experiments. I mean, we all have an intuitive experience of the natural world from our ordinary senses. I mean, I've had the good or strange fortune of also having sort of an additional sort of ruliological set of experiences from exploring kind of the world of simple programs. And that's kind of gives one a set of ways of thinking about things that are a little bit, perhaps a little alien to what we know from kind of our everyday experience. SSC, I can't parse the handle here. It says, this might be a dumb question, but is it possible for a Platonic ideal hypergraph that can be split into all Ruliad space? Not sure if that makes sense. I can't quite untangle that. I think the Ruliad is kind of the Platonic ideal in some sense. It's the thing that is the ultimate kind of the ultimate existing thing. I can't parse that question, sorry. Zero asks, what would Alan Turing think about your ideas, do you think? Well, I know a fair amount about Alan Turing. I know a bunch of people who knew him, or have known a bunch of people who knew him. I think one thing about Alan Turing is that he tended to be, I'll work on one project, then another project, then another project. And they didn't necessarily become big arcs of thought. I mean, he worked on the Turing machine in 1936. He worked on, practical cryptanalysis. He worked on practical computers. He worked on biology. He worked on sort of thinking about AI. These were all a little bit separate. He didn't really connect a lot of these things together. I think that the notion that, well, Alan Turing never simulated a Turing machine. The only Turing machines he looked at were Turing machines that he sort of abstractly wrote about in his papers. And by the way, they were full of bugs because he didn't have the intuition that there might be bugs and things like this. Nobody did. It was something you had to actually play with computers to get that idea that bugs were a ubiquitous thing. But I think the notion that you can make things from abstract things. I know Alan Turing was interested in that. He was interested in physics in that regard. He never learnt that much about kind of the physics that was known in the mid 20th century, but he was always, I think, curious about whether he was a very formal kind of minimalist thinker, um, and rather impressive at that. And I think that he certainly wondered whether things like quantum mechanics, he was curious about quantum mechanics. In a piece of trivia, there's a book about quantum mechanics by Dirac that he had a copy of, and um, through a chain of people, somebody gave me that book, Turing's copy of Dirac's quantum mechanics. And I wrote a piece actually about kind of tracking down sort of the provenance of that book, not least because when I leafed through the copy of the book, I found these pieces of paper which contained, among other things, pieces of mathematical logic. And so the immediate question was, did Alan Turing write these pieces of paper? The answer was no. In fact, they were written by a student of Alan Turing's called Robin Gandy. But that took quite a bit of sleuthing to find that out. But I think Turing was interested in this question of sort of what ultimately is there, what can be the ultimate foundations of things. And had Turing lived longer, I kind of think he would have ended up doing a bunch of things I ended up doing. But so it's kind of I had the fun of doing these things in the early 1980s, and they might otherwise have been done in the 1960s or something by an older Alan Turing, but he didn't live long enough to do that. All right. Well, I think we should wrap up here, but thank you for lots of interesting questions and comments. As I said, I am planning to start up some live streams of discussions with some professional philosophers, particularly people who know about the history of philosophy. And I think I haven't been involved in setting those up, but I think we may have some already set up. But looking for suggestions about people who we should try and include in those, and people would think would be interesting. And I'm sure it's going to give me quite a run for my money. I'm not I do have some experience in talking to philosophers from when I was 10 years old and things like that, but that's a while ago. So I'm always a bit and maybe I was spoiled by the fact that I knew a bunch of sort of Oxford philosophers of the 1960s and early 1970s at a time when that was a pretty pretty strong school of philosophy. And so my image of sort of how philosophers think about things, and how quickly they can go through arguments, it's probably based a little bit on the 10-year-old me talking to the 50-year-old high-end Oxford philosopher of that time. And maybe it's like one of these things where I'm a little bit, it's like when you go back to places you saw when you were a kid and you say, boy, this is a lot smaller than I remember it. Maybe that'll be the experience. I'm not sure, but I'm looking forward to having a chance to have some really interesting intellectual discussions around philosophy in the coming time. So until then, thanks for joining me, and bye for now.